Hello. In this video I'm going to be building a yak daemon from scratch. In this case it'll be a daemon to communicate with a programmable syringe pump, ne1000 from New Era pump systems. You can see over here I have a little running video, live video, hello, of the pump. And yeah, we'll go through in several stages, and I'll try to bring you along with all the little nitty-gritty details it takes to actually go from nothing to a working yak daemon. In this case, being a syringe pump, it's basically a single motor, so it's going to be a fairly simple daemon. So I'm going to start out as I would with any brand new hardware, just by verifying that I am able to communicate with the device from my computer from Python. I looked a little bit at this syringe pump already, and I've seen that it's an RS-232 program, RS-232 interface. So it documents the RS-232 command set here in the manual. So I just go down and we can take a look here. So it's got different baud rates. I've happened to check this particular pump is running at 19200, I'm pretty sure. It's got a 10-bit frame, so it's got the start bit and the stop bit. So it looks like it's going to be a fairly typical device here for RS-232. So I'm just going to try and choose just some command that I can start out with to see if I can communicate with the pump at all. And I looked through it before, and I think I'm going to start with this command run. So run just starts the pumping program, whatever that program may be. So in this case, I've got it programmed to, just dispense, or I guess withdraw some random number of milliliters. And we'll see if we can get that to happen from a command from our computer here. So I've got a USB to RS-232 adapter plugged in here to my machine. So let's just see if I can see that. Okay, I think it should be this device. So if I drop into Python and I make a serial object for that port, and I remember my faster baud rate, then I should be able to just send, let's see, I think this is pump 0, run. And you might be able to hear it or see it. It's quite slow, but actually it is withdrawing, so it's moving towards my arm here. And it's withdrawing and withdrawing. Let's just see if I can get it to stop. Yep. And you would certainly be able to see the little LED indicating pumping there. Stop. Looks like it has some idea that it's within a procedure, so when you stop it, it just pause. Yeah. So there's some complex state to deal with here, but we don't necessarily have to worry about that for our daemon. Okay, so I'm pretty happy with that. And given that it's just such an incredibly simple device, you know, it's just a single motor, I actually feel ready to begin working with my daemon. So the next stage is to use a cookie cutter to create all of the boilerplate, all of the files you need but don't need to be necessarily all that custom for our new daemon. Cookie Cutter is a very popular project that allows developers to create templates that other people can use to generate new projects by answering a few simple questions. So you can come to Cookie Cutter for installation instructions. Most of you will probably just need to do conda install Cookie Cutter. And we provide a template for a Python daemon, a Cookie Cutter template. So all I need to do for my new daemon here is copy the URL to this Cookie Cutter, and then within my source directory, where I have all of my other projects as well, I'm just going to say Cookie Cutter and then that URL. In my case, I've downloaded it before, so I'm going to let it re-download it. And it's going to ask me a bunch of questions. If I just press enter, it will use the default in the square brackets. Otherwise, I can type what I want here. So I'm going to type my name, my email. Customary thing to do is to give the project the name based on the manufacturer of the device. That way, all the daemons for a given manufacturer can kind of be put together into the same package. That's fine. It's also fine. I'm just going to call it Yak Daemons for New Era Pump Systems Hardware. Initial version for my package. LGPL is an OK license for me. Don't want to use PyTest. And let's call it new-era-ne1000. NE1000 being the model of the syringe pump we're working with today. Okay. Okay. Great. So what that's done is it's actually created a new directory on my within my source directory here, yakd new era, and it's created all of these different files in that directory. Here, let's look at it over here in my file browser here. Here it is. So what are these files? Well, like I said, these are all the boilerplate, all of the kind of starting out files that you just need to get your Python package off the ground. Crucially, there's pyproject.toml. So this is the file that defines the project as a Python module, you know, something we can install and import. And crucially for our usage as Yak developers here, it also defines this entry point. So you may be familiar with launching Yak daemons from the command line or enabling them. Well, this is how that works. This maps that command line command that you would type in into a particular module and a particular function that gets executed by Python when you call that command. There's also a little README we create for you. And then within that subdirectory in here, crucially, there's two files. There's this toml file. We're going to be using this in the next stage to define the protocol for our daemon. We'll talk a lot more about what that means later. And then there's this Python file, and this is where we're going to be writing the class that actually implements the behavior. You know, it's going to be sending and processing the RS-232 commands that we were playing with in the last part. So that's the cookie cutter, and now we're ready to start actually filling in what's unique about our daemon. The next step in the creation of our daemon is actually to define the protocol. You know, what is a protocol? Well, we actually have to talk about how clients and daemons communicate over TCP within the Yak ecosystem. And the answer is that we follow the Avro specification. Avro is a strategy for serializing types, a lot like JSON or message pack. Unlike JSON, Avro tries to serialize data as compactly as possible, so your data structures are transmitted over the wire in as few bytes as possible. But in addition to that, Avro's specification actually defines this concept of a protocol, which fully describe remote procedure call interfaces, like the Yak client daemon interface. And protocols are defined as these JSON payloads, and when a client and a daemon, referred to here as a caller and responder, first connect in Yak or in Avro, the daemon actually gives the client its entire protocol, and that protocol defines entirely what messages, you know, what remote procedures are available within that daemon, and exactly what the arguments to those are and what types of data can be gotten in response. And importantly, once the client has gotten that information upon first connection, it doesn't need to get that information again. The protocol of a daemon is statically defined, and in fact it's statically defined at time of writing the daemon, what we're doing right now. So basically our goal is to create this JSON payload that entirely defines the interface that clients will use to control our syringe pump. Now, of course, that interface is going to be much more complicated than just a simple single message. So we've actually created a tool that allows you to capitalize on the traits system that Yak, at the core of Yak, to help you create your protocol without having to write out everything by hand. So this little command line tool, Yak traits, documented at this position, has this key feature, Yak traits compose, which takes this toml file and generates the AVPR file. This is simply the JSON payload Avro protocol file. So actually the specification of that toml file is defined formally here, but it's pretty intuitive. Let's go start working with it now. So this toml file was generated automatically by the cookie cutter in the last step. If you look, so here I am, I've got this toml file here. And if I just use yak traits right now, and I just press enter, it'll spit all of this information to standard out. This huge JSON payload might be more useful to write that to a file. So if I open that, I can see that it's got a whole bunch of information, much more than might be implied just by how terse this TOML file is. It's got all these config options. It's got all these messages, like for example, busy here. It's saying that busy takes no arguments, request is empty, and it responds with a Boolean. And it even gives us this little clue, origin is daemon. So what yak traits is doing here to generate the ABPR is it's simply referring to the traits that we've specified in the TOML file, and it's using the fact that the traits are fully described to know what messages and config options and state options are implied by compliance with those traits. If you're curious, actually, you can see here in the yak traits repository, the source code for that command line application, that, let's see, we were looking at the busy message. It's actually defined here in this TOML. So this is like the source of truth, as it were, for that message. So you can see that if we can just define our traits, then a lot of the work will actually already be done for us, and the protocol will be mostly complete. Here's the current list of traits within the Yak ecosystem. I've thought about it a little bit in advance, and I think that this syringe pump should have 4 traits in addition to the core is daemon trait. I think it should clearly have the has position trait. This is a very core trait that any simple piece of hardware that can be sent to a destination and then have its position read back should implement. You can see it's got a minimal set of messages here, and it's got a ton of daemons already implementing that trait. I think we should implement has limits, uses serial, and uses UART as well. Remember that we're communicating with this hardware over RS-232. So let's fill that out for a moment here. So has position, has limits, uses serial, and uses UART. Once I save that file, if I regenerate the ABPR, you can see that I now have a whole bunch of new messages, new config options. So for example, set position is a new message that I now have thanks to the fact that I've implemented the has position trait. Now don't get too confused here. All we're doing is generating the ABPR. In the next section, we're actually going to write the Python implementation. We'll talk separately about that. But yak traits is very helpful for generating that full statically defined protocol that's so important for instructing clients how to interact with our daemons. Now, of course, like most hardware, the NE1000 has a little bit of behavior that's not perfectly captured by the traits themselves. So we're going to have some unique config and some unique messages that represent that unique behavior that this hardware has. first, I can say we're going to need a config option for the address. Remember that these syringe pumps can actually be daisy-chained together into a single RS-232 network, and the RS-232 commands have this simple integer address, it can be 0 through 9, that allows you to specify which of the pumps in that network you want to talk to. So RS new era address within RS-232 network, integer from 0 to 9. And I'm going to specify that the type is an integer. And I'm not going to give it a default because I want to force everyone who's using this daemon to explicitly provide me with an address. I don't see any reason why I don't see how any particular address is necessarily better than any other. So let's see. I also thought, you have to give the diameter of the syringe to be able to use volume units, which of course we do want to use. So I've got to specify that inside diameter of syringe. And let's see what else. This pump can actually think and speak in different types of units. If you look at the command for specifying the volume to be dispensed, it actually has the ability to specify units. And I think up here, let's see, where was that? So that can be one of microliters or milliliters. So, and we'll also specify rate units. So that's why I'm being explicit about volume here. Volume units. And this type is going to be a little bit more fancy. It's not just going to be something simple like an integer. Avro actually has a concept of enums. So these are where you want to have a choice between a limited, explicitly defined set of options. So we can do that like this. Oops. Not quite sure. I've forgotten my TOML format, so let's go back to here. Okay. So it is an equals sign. Type is enum, and then there's a comma. Okay. So basically, I'm just putting in this information, but of course I'm writing it in TOML instead of in JSON. Let's say name equals volume unit, and symbols equals and I'm going to actually write out the full text here because we have a weak preference in the Yak ecosystem for using unit strings that are compatible with the pint unit system. Let's see, it's listed here. So Pint is a very fancy unit system that does a lot of the heavy lifting for us if we're in Python. So, you know, microliter is a fine unit for pint. So, I'll say microliter and milliliter. Okay. So, and then volume units. So you can see how the Actrates package put that into our JSON payload for us. The other type of units is rate units. And actually, I did want to default, so that way we won't force everyone to necessarily specify units. So again, and this was specified again in the PDF here. I believe it was its own. Yes. So there's 4 options there. And again, I'm going to fully write them out. Okay. Just one more thing that I had picked out as something to put into unique configuration for our daemon, and that is low noise mode. I think I must have gone past it. Yeah. This one's a little bit of a mystery to me, but set query low motor noise mode increases motor stepping resolution. Seems like something people might want to change. So I'm just gonna low noise motor mode let's just check primitive types. Oh, I'm wrong. It's not bool, it's boolean. Great. Okay, and that's our config. So those are the options that people will be allowed to define in that little file that will then get read in and applied when our daemons start running. We'll see that later. Of course, in addition to these 5 unique options, there's a bunch of other options that are specified by the config by the traits. Okay, so now state is a very useful tool for being able to stash away any information that you as the daemon writer need to be available to you to kind of remember during periods where the daemon might be off or perhaps the machine is restarted. For example, certain motors don't have encoders or limit switches, so the only way to know where they are is just to remember how far they've moved since you did set their position explicitly. And that would be a case where you really need to care about storing that position to state and then reinitializing your daemon when it starts up based on that stored position. Thankfully for our syringe pump here, as far as I can tell, absolutely everything about it is able to be queried off of the hardware itself. The hardware has some non-volatile memory. Seems great. So I'm going to say we just don't need any unique state for this daemon. Okay. Messages are, they are the procedures that can be called, the functions that you can call remotely themselves. So I thought we should probably implement a message for purge and a message for prime, which is the opposite of purging. Yeah, so actually the command we'll send to the pump is PUR either way, but I think for our YAC interface, specifying it explicitly in two different messages would be great. So purge means that we are going to fully inject the pump. And let's go back to YAC traits, config, messages. So I need to define a request. So in this case, my request is just going to be empty. Don't need any arguments to purge. And that's it. So fully withdraw. Okay. And then I also wanted to be able to control the rate itself, not the rate units, but the rate itself dynamically over the YAC interface. So I'm going to implement a get rate message. And in that case, I will need, let's take a look at that. Yeah. Single double, let's say, which is the rate itself. And no response. None of these have a response, actually. That's if you want some piece of information to be, returned from the daemon to the client. Okay. And then finally, I'm actually going to implement something called a field. let's go back and look at fields. Actually defined in this yep 111. So in this case, we'll do fields dot rate. So what fields are for are they're to signify to clients, especially graphical clients, that particular pairs of messages are logically tied together. So I have to say that there's this concept of rate. It has a type of double. Oh, I've mucked that up, haven't I? There you go. That makes more sense, right? So get rate will take no arguments, but it will respond. Set rate will just have the request of what the new rate should be. And then getter be get rate, setter will be set rate, dynamic. I believe that having a setter means that dynamic is implied true. Oh, and then kind is one of, let's see, kind is normal, meaning that you don't necessarily have to display this all the time. Yeah, I think that's right. So now if I generate my ABPR, I have all that information. Okay, with the static protocol done, now we're ready to begin implementing the actual Python, which will send and receive the RS-232 commands and communicate with our hardware. So we're going to use yakdcore here. It's defined in this repository. And that package defines kind of an async IO based implementation of a yak daemon using one class for each yak trait, which makes it very flexible and appropriate for building yak daemons on top of. For example, the hasPosition class has these simple methods, some of which you won't need to overload at all, and others of which you must implement, like setPosition here is marked as something that you must implement. So let's start. Oh, I wanted to mention that in addition to those classes, there's also this little submodule that contains a simple wrapper around the same serial interface that we used at the beginning to communicate with hardware. This simple wrapper just defines some methods that are a little bit more convenient to use in an asynchronous context. So we're going to be using those same traits that we thought about before. So that's hasPosition, hasLimits, uses serial, uses uart, aserial. Oh, and I shouldn't forget, because we are using that serial package here, we will need to explicitly mark it as a dependency. So that's done in the pyproject.toml file, pyserial. Great. Okay, and now I just need to mix all of these classes into my daemon defining class. Because of the way that Python does multiple inheritance, I do need to think a little bit about the order that I write this. So uses uart, for example, because it depends on the uses serial class, must come earlier than the uses serial class here. Same with has limits, must become earlier than has position, and is daemon, of course, must be last. Now, I can't, just due to time, I'm not going to show you my entire process of writing this daemon, you know, hacking it together, trying it out. But I thought we'd just get started here together by implementing at least one method and getting hardware to move. And then we'll come back once I'm done and it's polished, and we'll go through and talk about exactly how it works. So I thought the one method we might implement together would be purge. Pretty easy. It's pretty easy to tell whether that's actually going to work. So I know I'm going to want to create a serial object as an attribute here. Pulling information out of config to feed into that serial object. And let's see, I think that's all the init I need at the moment. Not going to worry about update state. So purge. Remember, it takes no arguments, and all it really needs to do is just send a single serial command. So I'm going to use fstrings here. Serial command should start with the address, and then there's a space, and then I think it's per, and then carriage return. Yeah, I think that might be it. So let's start from there and try to install and use it, see what bugs we come across, and just defeat them until we have first successful communication via our daemon. So hopping over to the command line here, I'm in the same directory as my pyproject.toml here. And what I need to do is install my package so that that entry point that's defined in pyproject.toml is available to me. And I'm going to use a tool called flit to do that. So flit install -s. You might need a slightly different command on Windows. Check it out. But should go through, make sure all of my dependencies are installed, and install my entry point. So let's try it out. Great. So I'm starting to begin the daemon, but it's complaining, as it should, that there's no configuration file. So we know how to create configuration files. new-era-ne1000. Let's call it just pump. So I'll give it my TCP port that the yak daemon will serve on. I'll give it my serial port. I'll give it my baud rate. I'll give it my address, remember, and diameter, I believe, was the final required config parameter to start one of these daemons. And because I've already defined all of those things in the protocol, I do need them now, even though I'm only interested in purge in this initial implementation. So, okay, it's not complaining about config anymore, but it is complaining that I haven't even attempted to implement these abstract methods, set position and direct serial write. So it looks like I can't get away without doing that. But I don't need to actually implement them yet. I just need to define the signatures. Oop, that's not right. Set position. Okay, for the first time, my daemon is running without immediately crashing at startup. So let's take a look here. Let's drop into Python. $39,000. Oop. Spelling error. Let's do purge. Type error in message purge. Uh-oh. Ah, I see what I've done. Silly me, I didn't even call write. I'm just using call itself. So restart the daemon. Try again. Ah, there we go. Not quite sure why I needed to send the command twice. But that's just, let's stop that. That's just one example of many little debugging things I'm going to go into now, but I won't bring you along and torture you guys with that. So next time we're together, I should have a fully working initial implementation. Okay, I've got a daemon here. Took me a while of fiddling around, as you might imagine. Ended up being a little bit more complicated piece of hardware than maybe I would have liked, especially for this example that we're going to build together. But maybe that's good. You guys can see a few tricks of how to work around some of the idiosyncrasies of real hardware. Anyway, let's take a look at what we've got here and see a little demo. So, right at the top here, I've got some regex statements. This first one allows me to extract the infused and withdrawn volume out of the syntax that the pump responds to when I query it for its dispensed volumes. And the second one allows me to extract the rate when I query the pump for its rate. Then I have just some hard-coded dictionaries here mapping our pint units that we prefer to use when possible to the pump specific units defined by the manual. Okay, so this is the same class we were working with before. Obviously it's got a lot more filled out for it. So let's take a look. You can see 157 lines of code, or lines in the file, I should say. But if we go through it slowly, I hope, it'll make sense. So init is the method that runs when we first start our daemon. You can see we create the serial object just like before. I did add in an end of line here, provide that argument. We'll see how that's useful later. I have a little attribute rate here that I'm going to use to kind of cache the rate that I know my pump to be operating at. I have an attribute, Boolean attribute purging, initialized as false. And one of the quirks that I experienced with this pump is that after turning on for the first time, it totally ignores the first RS-232 command that it sees. So to get it so that it doesn't ignore a command we actually care about, right at the beginning here, we're going to send a command to read out the dispensed volumes, and then for sure the next time it'll respond. And then finally, now this is some async IO style syntax. We are going to add the task get rate to the async IO event loop. So basically that means that this little method is going to be executed as soon as the loop gets around to it, which will be pretty quick. Okay, let's just go method by method here. Close. Here we just close our serial object. That's especially nice to do in like a Windows setting where serial objects might be blocking. Close is defined. I'm going to show you guys where these things are as we go. Close is defined by the isDaemon class, which is the most upstream parent. And you can see that it's called by our shutdown method. So basically that just gives us an opportunity as daemon authors to put some special code there when our daemons are shutting down cleanly. Direct serial write. It's defined by the uses serial trait, and as such it's written as something that must be implemented. It's an abstract method of the uses serial parent class. Message is bytes, and I see that now. I should mark that because I actually messed that up. Message will already be encoded. Get rate simply returns that cached attribute rate that we know and love. And underscore get rate is going to write the RAT command to the pump, get out these three pieces of information from its response. It's going to use regex, like we saw, to match and extract the rate information. And you'll see a lot of try and excepts throughout this code. You know, real hardware is inconsistent. I have RS-232 to USB converters in the loop here. Sometimes, you know, bits get flipped and stuff like that. You might expect more than you would think to just get junk data. So the try except pattern is going to be a very important one as you work with real hardware and try to make a robust daemon implementation of it. Prime, defined uniquely by this daemon. Here we see the logger for the first time. So that's defined by the isDaemon class again. And we can simply call the logger in this way to spit out information to standard out so that it can be logged by either your operating system logging system, if your operating system has such a thing, or can be simply logged to a file as defined in the Yak enhancement proposal that discusses logging. We flip busy to true when we begin priming, and all that a prime is a purge where the direction is withdraw. So set direction to withdraw and then purge. Purge, on the other hand, is much the same, except you set the direction to infuse before calling purge. The other difference is that we flip the state of this purging attribute to true. We'll see what that means later. Set position. This method is interacted with by the upstream class again. Has position. So it's marked as an abstract method. It must be defined by children. And we can see that the set position method that's called directly over the Yak interface flips busy to true, sets the destination, and then calls this synchronous underscore set position method. In turn, in this particular case, we move that into the event loop so it can be done asynchronously. So we create the task for a set position. And in a set position, what we do is basically just send a whole bunch of commands, like 4 commands, to the pump that together define the procedure for moving the amount we need to move relative to our current position in the units we care about, and then actually beginning that procedure using run. So we explicitly stop any ongoing procedures. We calculate the direction that we need to go, and we calculate the amount of volume we need from our current position. And then we say, please inject or withdraw or infuse that volume and run. The only other quirk, and it is a weird quirk, is that the way that this volume information is encoded into ASCII strings to be carried over the RS-232 interface, you can only have 5 characters. So that means a volume of 100,000 or a volume of less than 1 milliunit is not representable using the ASCII interface that the pump uses. So that's how we have some code here to ensure that those numbers don't get through. And then also here we have some special formatting and some string truncation to make sure that all of that works exactly as the pump needs it to work. Set rate, very similar. Okay, update state. Now this is a big one that's going to be seen again and again in all daemons. In the upstream parent class is daemon. Update state is actually added explicitly to the event loop. And what yakd core, the package, expects you to do is define some task in that method that's going to run forever and just deal with maintaining all of the state for your daemon, in this case the position and the destination. So we have a outermost while true, so everything inside of here is going to run forever. It's never going to exit this while loop. And then we have an inner while true that only breaks if busy is false. So this inner while loop is going to run and run and run as long as the pump continues to move, continues to be busy, and then it's going to release once busy becomes false and move on to these other steps. So let's look a little bit closer. What this inner loop does, the busy loop, is it asks the pump for its dispensed volumes, parses that out. It looks for alarms from the pump, and if it sees it, it tries again. Logs. Looks again for weird situations. If it sees them, tries again. Now, by the time it's gotten to here, we're pretty sure we have good communication with the pump. Nothing's gotten corrupted along the way. And it looks for a prompt in S and P. So stopped and paused are the two states of the pump that we're going to map to busy being false. Everything else implies busy remains true. So that's what we do here. Oops, don't want that print statement. We pull out the infused and withdrawn volumes, use it to update the position, and we have try except again. And then if busy actually became false, we break. Now, purging. If we were purging, if this motion that we were previously in was a purging motion, now that busy has released, we're assumed that we're done with our purge. So we're going to explicitly write stop, which is a strange quirk of how purging works for this pump. We're going to set our purging attribute to false, and we're going to zero out our position and destination. So that means that if the pump has fully infused, it has no more volume, no more liquid within the syringe, that means that we have zero volume, zero for our position and our destination. It's kind of like home for the pump. And then we're messing with the stored values for infused and withdrawn inside the pump. That's kind of matched here with how we extract it and we add it in together to maintain our position information. And then finally, this block of code, we wait for the busy signal to flip to true or for a timeout of 5 seconds, whichever happens first. So again, within isDaemon.py, that busy signal. So underscore busy is actually a property that has a setter so that every time its value is changed, we have an opportunity to set or clear these async IO signals. So that means that if anywhere in the code the state of busy is changed, this will immediately get called and it'll move on and go into this quick loop, monitoring the pump while busy remains true. Otherwise, it'll simply wait for 5 seconds and then run through this once just to see if anything's changed. Finally, you might have noticed that in many cases I have this simplified await self.write syntax, and this is the method that we wrote custom for this pump to actually do that. You can see that it uses a write then read line, which is a command that fills up a buffer with all of the information being returned by the pump until it sees that crucial end of line character that we defined up here. And then it returns that whole response as one object, which is very convenient. And then we simply parse it out according to all the little details of how that response works within the manual. So that's quite a lot, but as you can see, it's all just dealing with the nature of the RS-232 interface that this pump defines. Let's check it out really quick. So I can launch my daemon here in the foreground. I'll put the log level to debug so we can see as much information as possible here in the console. What we'll see is that it is querying the volume here. So this infused and withdrawn volume here every 5 seconds. That's happening because of the timeout here. So the position is 10. So if I set the position to 11, it should move to have 1 unit more additional liquid in the syringe. So it should move towards me. And I can watch it actually update. Let's move it a little bit further here. Let's move it all the way to 15. There's a little bit of the delay, again, idiosyncratic nature of the pump, but now I can see the get position and I can watch it update in real time. So if I was making a graphical client or something, the user would be able to see that as it's happening. And there it goes. And let's see, what else can I do? The other thing that I can do, if we remind ourselves of what the parent has position class looks like, we can see it implements set relative. Of course, that's part of the trait for has position. But we can use that here as well. So if we want to move, let's just say just 0.5 millimeter this way, so that would be more negative, lower values. So I can do set relative 0.5. And it gets to 14.5, just like we expect. So basic demonstration, but yeah, it's a working daemon. I'm 100% sure that I have made all types of mistakes and oversights, and there's probably bugs. It's early days for this hardware support in Yak, right? But nonetheless, for my next step, I'm going to get this daemon onto the GitLab repo. I'm going to get it published onto PyPI and Conda, and I'm going to put it onto our shared documentation website, yak.fyi. Not because I think it's done, but because I think it's good enough to be moved into the laboratory and start to be used on a daily basis and iterated on along with all the other Yak daemons that are going to be part of, you know, whatever instrument it's going to be incorporated into. So here's our repository for our New Era pump system daemons on GitLab. If you're building Yak daemons, feel free to ask permission to make them within the Yak repository, Yak group. We have all these different daemons here. People are kind of building collaboratively. It's just good to be able to keep them all under the same roof so people can see what each other are working on and help each other out. So that's what I've done here. Yak New Era is in the Yak organization. Here's all of our files. Here's that class that we just looked at. And then I'd also like to upload my daemon to Conda and to PyPI. Won't go through that here, but feel free to reach out if you need help with that. And then I want to upload the daemon so it appears here on Yakko FII, which I've already done. Here it is, new-era-ne1000. So to do that, I have to add just a few more pieces of information to that toml file we started with, where we defined the protocol. I'm going to update the doc to make it meaningful. That's going to appear here. And then I'm also going to update this hardware list. So that's going to help the website know which daemons are compatible with which pieces of hardware. And once I'm ready to actually add my new daemon to our website here, I'm going to make a PR to Yak FYI, updating perhaps 3 places. Firstly, I'm going to add my ABPR file to this directory, the daemons directory here. Luckily, once it's added, we have a bot that's going to look at PyPI for any changes and update it automatically. So you don't have to worry about keeping it updated once you add it. Then I'm also going to update known-hardware.toml. So this is where that metadata comes in, corresponding to the string we have here that's going to make this information appear. You know, a link to the manufacturer, that kind of stuff. Pretty basic, but nice to have. And then finally, I'm going to update known packages. So that's what's going to make our package appear here. And you can see that our package is not yet on Conda. Still working on that, have to go through a review process. Yeah, and again, the whole idea is that it's not done. This is something to iterate on and move towards increasingly better hardware support for all of these different daemons. Thanks for watching this somewhat rambly video, and feel free to reach out with any questions. Bye.